There will be a delay of 15-20 seconds, sir. So, but you can continue.
Right.
Just
Questions answer.
yeah, audio is coming, sir.
Okay, fantastic.
So we are live, sir. You can introduce and start. You can start with those questions, sir, and then whenever they post, you can answer to that. And then if general questions come, you can simply skip it, or if you want to answer, you can answer, sir.
Okay.
Yes, sir. Please go ahead, sir.
Good evening. This is Jayant Singh, the instructor of this particular course, Chemical Engineering Thermodynamics. So thank you for posing some questions, which I have now offline. So the first question was from Paki Balu, and the question is, when will the vapor-liquid equilibrium be taught? In principle, we have already discussed that vapor-liquid equilibrium, that essentially the conditions of that. But if the question is pertaining that how to use the fugacity and activity coefficient to come up with the equilibrium phase diagram, that's something which we are going to start in the week 9. That means something should be within 2 weeks. Okay. So essentially, once we understand the fugacity which is relevant for the gas phase and the activity which is relevant for the liquid phase, then subsequently the chemical coefficient equilibria and the temperature and the pressure, well, we are going to use that and solve the equations in order to find the phase equilibrium. So that exercise we are going to do that soon, and at this point we are making the foundation strong to exercise those conditions. Okay. The second question, which is from Ketan Jangir, and he mentioned about that. Sir, I've studied chemical engineering thermodynamics, but what is he's facing some difficulty in understanding the subject because of the notations, and this is very unfortunate when it comes to thermodynamics, because we keep changing the notations if you go from one textbook to another textbook. I was trying to emphasize that the variables which we are going to use is something which has more meaning, and sometimes I do have used it a little different from the usual textbook. So my inspiration is basically from engineering and chemical thermodynamics. Okay, and this is by Ville. However, I've been also being using the initial part of the discussions, which were mainly from Callan Herbert's book. Okay, and if you happen to get hold of that, that's on the thermodynamics and introduction to thermostatistics, second edition. So you can use, you can also go through that. That is a beautiful way of explaining thermodynamics. So some notation is probably a little different from that. But what I try to do that is notation is more or less we kept the similar throughout this course, and wherever I change it, I try to emphasize, and possibly if not, then again you can point it to me so that I can help you in understanding those changes in the notations, or in general the difference if there is someone. But as I said, the notations keep changing, and hence understanding the fundamentals of the variables becomes an extremely important part, so that we do not get confused with the change in the notations. Okay, but so just look at this Callan Herbert's book on thermodynamics, and as well as the Koreski, which is the textbook. And actually, if you are looking from like a week 6th or 7th onward, you will see that more or less we are trying to follow the course. Okay, in the initial part I try to avoid that, because as I mentioned earlier, that if you have done engineering thermodynamics, then you have gone through the more details in the the engines and different cycles, and hence I did not emphasize too much as in the case of the book, which the textbook. However, I try to emphasize those things which is I find relevant for to build up the fundamentals of thermodynamics, particularly the chemical engineering thermodynamics. So I'll take up another question, and this is from someone who is a retired scientist, and he says that what would be the format of exam? Only objective or 3 hours? So mostly we do have little bit of objective questions, but subjective questions are also there. Of course, the answers are in terms of multiple options, but you need to make use of the fundamentals and all the equations which you have learned and apply to the conditions which has been posed in the questions and solve it. But there will be basically some questions which will be true and false, and some questions which will be more detailed, so that we can judge whether you have in-depth understanding of the subject or not. And this is something which is taken usually care by the NPTEL main office. Okay. The second question was this concavity and convexity of the thermodynamic parameters and the second derivative behavior. The clarification will be helpful. Now, this is relevant, that is the shape of the potential function is relevant to identify the stability of the system. We talked about concavity and the convexity related to the entropy function and energy functions. So when you talk about energy as such, you are looking at typically that your system should have a convex behavior. Okay, particularly because you imagine the conditions of a drop, or let's say a ball in some kind of hole, or some kind of where it's difficult to get out of it. So the system also energetically doesn't just comes out from the a certain state unless you provide external means of changing the equilibrium state. Now if you think from that point of view, that means basically the system is stable when the second derivative of the potential energy function is greater than zero, and that brings up this convexity of the energy function. It means very simple that if you consider the function and if you take a slope or tangent at each point, then the function should be above the tangent if it is stable. If it is not above the tangent, that will be the state of instability. And those regions which would be could be concentration, because if you plot u as a function of, let's say, density or something like that, or some other state function, essentially those regions where the surface is above where the surface is below the tangent, then those cases are going to be unstable. So these are the concepts which we try to introduce. Now for the case of entropy, if you take entropy as a measure to identify stability, then you have to worry about the concavity of that. In the sense that if you take a slope, then the tangent should be above the surface of the entropy, and that would indicate the stability, and otherwise it will be unstable. So these are the concept which essentially is nothing but the mathematical function of the nature of the potential function. So if you understand the potential function, that the shape is reflective of the stability, then you can easily visually understand that which are the region is going to be stable, which are the region is going to be unstable or metastable. So we try to use those concepts in order to provide the mathematical descriptions of the stability and instability. Okay, otherwise it's a straightforward exercise, and something which we are going to look at it when we discuss about the mixtures and the gas-free energy and so forth. So when you look into when we are going to talk about this vapor liquid equilibria and something like that, and in the later stage we will be getting this kind of issues or questions, and we'll try to solve that using the same functional forms. Okay, and so this will become also important actually in the later part when we are trying to calculate the phase diagrams also. So these are the important mathematical constraints which will help us to identify the phase diagram. The other question which was asked was that what about the phase rule? No mention about this in lecture. So actually we did discuss about the phase rule. It was in week 6, lecture 1. I did not try deliberately to elaborate more. So we did derive it using the basic constraints of the equilibrium, where we consider the temperature, pressure, and the chemical equality of different components, and phases using the constraints and the basic thermodynamic equilibrium. Okay, and then you have this Gibbs Duhem relation, which is a constraint also. So we obtain this information. So that's there in lecture 1, but we are not we haven't used as an example to do a lot of exercise. So please look at that. The other question, which is very interesting actually, is what is the role of thermodynamics in chemical engineering? And that's a profound question. The reason it is profound is most of the things which we see in the daily life is something which, particularly when you talk about chemicals or fluid, it is mostly there are things which are changing. For example, like there's a flow. You can easily see the flow, but which is static, you do not usually appreciate because it's static. For example, water in a glass, static. What is so important in as far as the chemical engineering is concerned. The important is that you are aware of the state, particularly for the case of water, you know that. But if you are interested to, let's say, start a chemical industry on a certain components which is new, or for that matter, if you want to separate two components, okay, essentially using, let's say, distillation column or some other means, then you should be aware of the energy required in order to separate, or particularly the conditions where the state is stable in order for you to work on it. For that matter, let's say you talk about some kind of a chemical additives which will change a state from one kind of a structure to another kind of structure. And these are very relevant questions because these are the things which surfactant industry works on it. These are the things which a petroleum industry works on it. Without the information of the thermodynamic property, one cannot design the distillation column. One cannot operate the appropriate heat or the boilers which is necessary for changing the state from liquid state to the vapor state. Or for that matter, you cannot provide the appropriate information for the condenser to change the state. So you need a latent heat information. You need the phase diagrams. You need thermodynamic properties in order to design optimally. Okay, so thus the thermodynamic informations play integral part of the design of all those industries which where where the materials are involved, where the fluids are involved. So I think that hopefully would address that this is extremely important subject. Phase diagram, on the other hand, is a wider implication. Is not just relevant in chemical engineering, but in many physics and material sciences. So what we learned as a phase diagram, though we are going to do only liquid vapor and liquid, but the implications are wide range, and hence understanding how to develop the phase diagram using analytical means, which we are going to use equation of state and activity models, is going to have probably more valuable additions for you as a chemical engineer, because once you know that, you would appreciate what is there, let's say, in Aspen software, or for that matter, if you want to generate a new phase diagram which is not there in those things, how do you generate, what kind of approximations you can consider. So these are the things which are extremely useful for you as a chemical engineer. Okay. All right. So these were the questions which was posed. If you have a specific question, then you can ask now.
They are yet to post their queries, sir. Let's wait for some time, sir. So would you like to have some coffee or tea, sir?
That's fine. Water is fine.
Four people are watching, sir, but they are not at all asking questions. Let's wait for 5 minutes, sir.
So once again, if you have any questions, please you can write it. Okay, I would be happy to address the questions. So what you should have? Wait for more.
Wait for 2 minutes, sir. In case
Ah.
if they are not asking, we will end the session, sir. I already messaged
Yeah,
them.
I think you mentioned.
Yes, sir.
We'll wait. I think there will be some people.
Right, sir. Yeah.
Once again, if you have some questions, please shoot. I'm here to address those. If you have some difficulty in some aspect of the course till now, please be free to ask question. So, do you have any other live session?
Today, no other live session, sir. Tomorrow we are having, sir.
But you have more than one live session or one?
We can have one more session also, 1 or 2 session also, sir, depending upon the availability of studio slots, sir.
Yeah.
Yes.
I think we can stop because now.
I think we can answer. So we can conclude the session, and if they have any questions, they can write on the forum, sir.
Yeah.
That alone you can tell them, and we will wind up, sir.
So I think since there are no questions other than what I received as a separate list of question, so I'm going to stop it this particular session. I would encourage you to send questions on forum, or you can always write to me as a separate on email. I'll be happy to address those questions. So thank you for being here, and I will see you in the class soon. Okay.
Thank you, sir.